use this one. Oh, sorry. Good afternoon, everyone. The first author, Dirichlet, cannot attend the conference due to visa issues, so I present his work, Bench Effect Correction for Microbiome Data with Dirichlet-multinomial Regression. Present metagenomic sequencing technique equip us with the probability to quantify microbiome. And with the emergence of consortium projects such as the American Gut Project and the MedHit Project, we want to ask the question, can we pull samples from different studies and analyze them together? We know meta-analysis can improve the statistical power and reduce cohort-specific bias. But the question is, can we pull samples from different studies directly? Here is the example. We collect 4 colorectal cancer metagenomic studies. All these studies are sequenced in the same sequencing platform. To visualize the overall difference of microbiome composition for the control samples, we plot the first 2 principal coordinates in this figure. And we can see each dot represents the microbiome composition of a sample. And we can see for different cohorts, there is a significant difference between them. And we also use Promanova test to detect the difference between different cohorts. And the p-value is significant. We call the difference between different cohorts as a bench effect. Bench effect can be caused by different platform, reagents, or even experiments. And in most studies, the bench effect is even larger than the effects between the cases and the controls. Here is an example of Bacteroid vagatus. It's one of the most abundant bacteria in our gut. Here we first compare the 2 red curves. The difference between them represents the difference between controls and cases in the Australian cohort. And then, on the other hand, we compare the difference between the red curve and the the green curve in the left panel. We can see the difference between them represents the difference between 2 different cohorts, Australian cohorts and US cohorts. We can see the difference between 2 cohorts is even larger than the difference between cases and controls. Therefore, bench effect is severe, and it can even distort association between microbiome taxon and phenotype, and thus making it difficult to integrate studies directly. So our first target is to correct bench effect for microbiome data, and then we will identify the association between microbiome taxon and phenotype. Bench effects has been long aware of when doing the high throughput sequencing studies. There are a lot of existing methods to deal with bench effects for gene expression data. However, microbiome data has its own unique characteristics. Here we compare the characteristics between the microbiome data and the gene expression data. We focus on the second characteristics. When analyzing gene expression data, we usually assume that the expression level of different genes are independent. On the other hand, for microbiome data, the read count of different microbiome taxons are dependent. And usually the read count of all taxons is summed to a constant. And actually, the read count lies in a high-dimensional simplex. Here, I want to illustrate the effect of dependence a bit more. Here is a toy example. We have 6 species. In the control sample, the read count of all taxons is 12, and the total number of read counts is 72. When the person suffers from disease and become a case sample, the first 3 species increase, and then the total number of the read counts is 108. We want to compare the microbiome composition for the 2 conditions, cases and controls. We want to do the downsampling to make the total number of the read counts in the cases is same as that in the control. After downsampling, we can say the first two read counts doesn't change, but actually their amount in the person increase. So we call them a false negative. On the other hand, the last three species read counts decrease, but actually their amount doesn't change. So they are the false positive. So if we simply ignore the dependence between taxon, we will suffer from increased number of false discovery and false negative. Here is our model. The microbiome read counts Yij, I for batch effect, J for sample, and G for taxon. We assume Yij satisfies a Dirichlet-multinomial distribution with parameter gamma ij. And the gamma ij, we decompose gamma ij as the first term is alpha j. It represents the baseline for the J taxon. And the Zij is the phenotype of interest. Xij is a p-dimensional confounding vector such as age, gender, and BMI. And delta Ij is a bench effect variable. We want to correct bench effect by learning the value of delta Ij. Vj encodes the association between the phenotype and on the J's taxon. We want to detect whether or not there is an association between the taxon J and the phenotype. We use a Bayes approach to propose a spank and slide prior on Vj. Cj is an indicator to indicate whether or not the taxon J is associated with phenotype. If Cj have a high probability to equal to 1, we say the taxon J is associated with the phenotype. Then we threshold the probability Cj equal to 1 by using median probability model or controlling the Bayes false discovery rate at a target value. Here is a simulation study. The variable selection performance is evaluated by the precision and recall and the F1 score. We conduct sensitivity analysis and benchmark our method with some existing meta-analysis approach. First, we sample data with different overdispersion degrees. And we can see our method is the darkest one. It's not sensitive to the overdispersion. And then, since the microbiome taxon are dependent on each other, so we want to check whether or not our method have a robust performance when a group of abandoned taxon associated with phenotype. And we can see our method is very robust than other alternative methods. Here we apply our method to the for colorectal cancer studies mentioned before. We first test the goodness of fit. The correlation coefficient between the estimate value and the observed read counts is 0.8. So our model fits the real data well. And then our method identifies 6 species significantly associated with the cancer. All these species support by literature. And then to conclude, we propose a novel model to correct bench effect for microbiome data, and we capture some unique characteristic of microbiome taxon. The simulation study and real data analysis say our method fits the real data well and can outperform than some alternative existing method. We also We also prepared our package on the GitHub. It's available. If you are interested, you can check the source code. So that's all. Thanks for your attention.
Hey, my question is, I think you might have already read, there is a paper that came up, NCOM, in 2015. They showed that Dirichlet-multinomial is actually not a proper model for modeling microbiome data because theoretically it imposes negative correlation across all pairs. Did you think of that? And my second question is, how did you handle zero inflation in this case?
You mean the zero inflation? Yeah. In our proposed model, we can say that. Sorry. Even because we use the macro. The Dirichlet-multinomial distribution. So this distribution allows the variance of the distribution is very large. So there along some part is zero. So it can explain the zero inflate. And the detail actually I'm not clear about. If you can ask this question to the first author, yeah.
Okay, so
I think it just can be explained by the over-dispersion of the distribution property.
thank you very much. You could maybe continue.
Okay, great.